small bubbles into the larger bubbles.
Yeah.
And then coalescence or buoyancy issues.
Yeah.
Any feel on the sort of timescale that you've seen possible?
Well, yeah. So I think we talked a bit about this last time. So the diffusion is a slow process, and this is the thing. Often it's not sort of recognised as happening in the first, say, week of storage, but it is happening slowly. And then 2 or 3 months later, it's happened quite extensively, such that then you get coalescence because these bubbles are getting much, much larger, or they're rising to the surface. So it's kind of almost like a two-stage process, probably. The bubbles would be stable to coalescence at the size you form them, but the fact is that they grow by this other mechanism. So it's difficult to generalize, but the key thing really is what is your starting bubble size distribution. What percentage are below, are in the very small range, which I would classify as, say, 20 microns, something like that. So it really depends on what the bubble size distribution is at the beginning to try and predict how fast that will evolve. But you're talking about weeks generally, whereas coalescence can suddenly start to take off, and in a matter of days there could be catastrophic changes. So it's a bit difficult to generalize. But there's that initial bubble size distribution, which is going to be a key factor.
Right. So this is the thought you had around where you map R cubed versus time. You see this kind of linear progression of the diffusion and the acceleration once you hit coalescence.
Yes. In fact, I think I remembered after the call. I think it's radius versus time cubed. I can't remember which way around. But it's the Lifshitz-Slevzov theory of usually Ostwald-Reichning. I think it's size versus time cubed. But I can look that up, or you can look that up. But yeah, but I think you might learn a lot from just trying to do some observations on your samples at time intervals and see if you can identify whether it's disproportionation, shrinkage, and dissolution as the key mechanism, or indeed if you've got coalescence early on. I would guess it's the former. But it'd be good to really substantiate that. Either probably visually even do it, but if you've got enough measurements of size and did a plot, you could probably prove that it was shrinkage, dissolution, and not coalescence.
Because maybe
that would also give you enable you to maybe kind of predict as well the sort of what's going to happen. It's obviously difficult extrapolating, but you could maybe extrapolate a lifetime.
So we don't know a starting size or our distribution, correct?
Well, I mean, we know just based on rough optical microscopy. So what happens is if I take a sample of this finished tub, and if I kind of take a spoon and I scoop out the top layer and then look at the interior, and then I can try to measure some bubbles with using an optical microscope. And then I use some software to try to get a bubble size distribution that way. I know that we're in the 50 to 100 micron range after about a day, seemingly as a mean. And then over the next few days, it does seem to increase, and then eventually, maybe a week in. You start seeing I would say maybe within 3 or 4 days, the bubbles start becoming visible to the naked eye.
Some millimeter size.
Maybe hundreds of microns. That's what I've seen in the past with our stuff.
That will be typical of just simple sort of disproportionation or Ostwald-Reichning. That's what you would probably expect, starting that size range, and then beyond that you get rising and coalescence, so then you get really, really big balls. But that's without introducing any of these other mechanisms with this partial coalescence, and that should help to slow that down. But I think I said right at the beginning, I hope I made it clear at the beginning that the only way to stop this completely is the Pickering mechanism, where you have truly solid